Hello everybody. On behalf of the whole team, I'd like to thank you for the opportunity to hold this plenary talk here at the ISARC conference, where I present instructive human-robot collaboration, an augmented reality-based interface for intuitive, interactive, and coordinated task sharing between humans and robots in building construction, which is a novel method for augmented reality-informed human-machine collaboration. We argue that enabling the human's craft to coordinate or take over specific process parts, a significant increase in flexibility and robustness of automated workflows becomes feasible. I'm presenting this work on behalf of our team, which is working in the environment of the Cluster of Excellence at University of Stuttgart, the Cluster for Integrative Computational Design and Construction for Architecture. We are working within the Research Network 1 Multi-Story Buildings Integration Challenge, and the team that I'm part of, and which consists of architects, mechanical engineers, and computer scientists, works on Research Project 4, the CyberPhysical wood fabrication platform, where one of the central aims of our research is to provide fabrication methods for multi-story timber buildings which exceed the current limitations of the state-of-the-art, where many buildings are designed on a modular logic which can be fabricated very efficiently and with a high level of automation, but result in grid-based systems with a certain lack of flexibility. Because it seems, if we follow the study of Bertram and others, that much bigger part of the market lies in unique, complex, project-based buildings where a higher flexibility in floor planning is requested. This is why we switch from transportable building modules to transportable and flexible fabrication modules, which can even be brought on site to extend the capabilities of fabrication setups and which can be customized for the individual demands of specific fabrication ideas. And one way to do that is with the integration of human craft, not just to collaborate in the fabrication, but to instruct and control the robotic system. The current state of the art, as it is presented by the International Federation of Robotics, defines a level of collaboration based on the proximity of human and robot and the responsiveness of the system. So we see the 4 levels of collaboration, which are called coexistence, sequential collaboration, cooperation, and responsive collaboration. Recent work in architecture is taking a different approach and focuses on novel human-robot collaboration in experimental fabrication processes. For example, humans and robots work together, but as separate units with no communication between the human and the machine. Or human work as the instructor and the sensor-equipped robot executes the task as a smart tool. Or, also a third example, human and robots collaborate as fabrication units, but they do it usually with robots with a lower payload and with additional sensors, so-called cobots. With instructive human-robot collaboration, we integrate human craft and high level of automation processes, and augmented reality technology serves us in 3 ways. Number 1, to extend the skill set of a human. Number 2, to coordinate the fabrication process between the human and the machine, as we can see here. And number 3, to hand over the instruction to the human craft, who is not necessarily a programmer. Multi-unit task sharing is a method which derives from the conceptual approach of task skill-based fabrication planning. In this concept, a set of tasks which must be executed to produce a specific building system is formulated. These requests are compared with the skill set of adaptive and modular and therefore flexible fabrication setups. Such fabrication setups can consist of several fabrication units, which can be industrial robots and other automated machines, but also human craft. And this is how we facilitate the information from a specific building design to a fabrication system. It starts with a parametric model and a process simulation of the building design. A communication system is implemented through a server that can read the tasks and communicate the fabrication data to the units for the execution, which can be received either by a human client wearing a head-mounted display or a robotic fabrication system, which in our case consists of two robots, the PINP, what is the pick and place unit, and the GNM, which serves for gluing, nailing, and milling. We used this case study, a structure for a trade show stand which surrounded the timber fabrication platform to test this approach. We start with a building design and define a list of tasks which have to be executed. For example, the pick and place of the timber slats and the timber slat fixation. Also, the physics of the system, meaning we need a positioning accuracy of below plus minus 5 millimeters. We have to handle a weight of 1 kilogram plus the end effector, and we have to work within the confined workspace of 2.70 m by 2 m by 1 meter. Other crucial fabrication factors like speed were not specified in this case study. Here we see the execution of the PIMP robot picking and placing a timber slat and the GNM robot nailing the placed slats. The PIMP uses a linear gripper and the GNM a wood nail gun for the execution. All of the 51 clusters which generate the structure fit in the defined workspace between these two robots. And the robots easily handle the weight of the slats. Here we see the execution of the human picking and placing a timber slat and the fixing of the placed slat with a screw. This allows to correct the fixation task where the robot has failed, for example because of a split nail or an empty nail gun. The skilled craft, which is extended with the hole ends, enables an accurate placing of the slats. And the electric screwdriver enables the fixation. The workspace can be reached and all slats can be handled by the human. So both fabrication units, human and robots, are equally equipped to execute the task, but only the human has the control and skills to correct if something went wrong. With Wiser, we developed a tool for crafts-controlled task sharing, meaning that it enables to assign tasks to humans or robots, but also enables the human craft to control the fabrication workflow. Again, this can be an in programming unskilled worker. Here we see the main components from the perspective of the user. The task window, which is marked in red, shows the state of the fabrication. A timer is running and can be used to control time-sensitive operations, like gluing, among others. The task list in blue marked shows the set of all tasks and a selection window with the units these tasks are currently assigned to, but which can also be changed. And the digital twins of the workpiece in green and the robot in yellow can be visualized as well. Let's quickly recap while we have the fast forward video showing the cooperative fabrication process. With instructive human-robot collaboration, the developed setup introduced the first step into a new level of human-robot collaboration. The interface and communication strategy developed in its research successfully transfers the supervision and direct control of heavy payload 14-axis fabrication setups like the one that we see to the human coworker. The coordination works fully hand gesture based and requires no understanding in robot coding. Additional information like the digital twins of the module augment the human skill set. Currently, we are testing the setup and the fabrication of a new building system where several new points are under investigation. Number one, the in-depth control within the sequence for a high adaptivity, for example, for process intervention. Second, the development of a generalizable ontology for more complex fabrication setups. And third, the optimization of the interface with, for example, real-time update of the digital twins, object recognition, and combination of inside-out and outside-in tracking systems. With this short outlook, I thank you for listening, and now I'm looking forward to your questions or comments. You can also contact me on my email account that you can see there. Thank you.